Good morning, everyone. Last week, we talked about the orthogonal and orthonormal set. First, what is orthogonal? Orthogonal means that I have two vectors and their dot product, or sometimes we say that it is inner product, is 0. And if it is 0, then we say that these two vectors are orthogonal. And if your vectors divide by your magnitude or your norm, that will be a univector. And these univectors, if their dot product is also 0, then we say it is orthonormal. Okay. So if I have vectors, k vectors, they are orthogonal. Then I divide by each norm. And this new set is called orthonormal set. So orthonormal means that normal vector, right? So, univector. So their norm is 1. Okay, that's the difference between orthogonal and orthonormal. Now here, let's talk about the projections. What is projections? We say that the vector v1 is the projection of v on the vector w. And we write in this way, v1, and it's project the projection of v on w. So if I have a vector v, this is the vector v. And here we have a vector w. Now what is the vector v1? v1 is this vector. And here we have angle theta. And this is v2. v2 is v minus v1. Okay. Now, this is the vector v, and I also have a vector w. The vector v1 is the projection of v vector on w, which is v1, okay, here. So this vector projects to the direction of the vector w. Then what is the value for v1? So if I have a v dot product w, that means the norm of v times the norm of w cosine theta. So here you can see the norm or the magnitude of v cosine theta is the dot product divided by the norm of w. All right, if this is 30, right? Here is 5. Then this length should be, here is 30. Then this length is 5 times 1/2. Right? I think so, yeah. So it's like a 5 this length, okay, times cosine theta. You'll get the magnitude, okay? The length times cosine, you get the length of v1. And here you can see that I have w divided by its norm. If I have a vector divided by its norm, then it is a univector, right? So this is a univector. V dot product, the univector of w. And this is the magnitude of vector v projecting onto W. It's a magnitude, and I need a vector. So the vector v1 will be the magnitude. A vector, I need the magnitude and the direction. So here, the direction will be the unit vector in W. Okay? I need the magnitude and the vector. And why the vector is a unit vector? Remember that in the beginning, if I have a vector in the direction of f with a length 10, so I need the magnitude times the unit vector. Okay? So the magnitude times the unit vector. Here we can apply that. The magnitude times the unit vector. Okay. So the first note, v1, that's vector, has the same direction as w. If the angle between the vector v and vector w is less than 90 degrees. If it is greater than 90 degrees, then the direction of the vector v1 will be in the opposite direction of w. So if w is still here, and your vector v the angle is greater than 90 degrees. So my the direction of the v1 is in the opposite way. This is v1. And of course we still have v2. All right. And the vector v, we can express the vector v1 as a projection of the vector v on w. And this value, this vector, is a zero vector if and only if, what happens that we don't have a projection on w. So w is here, okay? No matter what v is, I always can have a projection, right? What if? Do we have a case that we don't have a projection? Unless this is perpendicular to this vector w, right? I cannot do any projection. So if and only if these two vectors are orthogonal. And we may you may see that the v is perpendicular to omega. Now, let's say the v and w, these two vectors are not zero vectors. Okay, then the projection of v on w, we'll write projection. No, I don't need the capital. So the projection of your vector v on W will be good. The magnitude times with a vector, the direction. And the vector v minus this projection, which will be v2. Okay, so this is v2. This is v2. v2 is orthogonal to v1, which is also orthogonal to W. Okay. Any questions? That's why we have a square. All right. So let's see this example. We have two vectors. Okay, I want to find v1, which is the projection of the vector v on vector W. So v1 is projection of v on W. Dot product divided by the norm square. And then we have the direction W, which is two times 1, 2, minus 3 times minus 1, 3, 1 times 3, 3. So 2 plus 3 plus 3. And the norm of W squared, there will be 1 square plus minus 1 square plus 3 square with the direction in W. Then you get 8 over 11. That's the magnitude and the direction. You can also find v2, which is perpendicular to W or orthogonal to W. So v2 is v minus v1. It'll be 1 over 11, 14, minus 25, and minus 13. Always remember that this is orthogonal to the vector W. Very important because later on we will use Gram-Schmidt's theory, okay, and we will use the concept of projection. Any questions? Right, so here, let's try this too. Okay, please find the projection on of V onto W. In your team, let's get the most fast 3 teams. Okay, if you finish that with the correct answer, the projection of V onto W, what is that vector? You see that from this example, you may have a magnitude and also the direction. This direction is just W, right? So I may need your magnitude and also your direction. Magnitude, direction. If you follow step, that you will see that this should be minus 11 over 30 W. And the second one should be 73 over 101 W. All right. Now let's talk about the planes. For the planes, how do we express the planes? Here I have a non-zero vector, and we call this vector n is as a normal vector, or this is normal to a plane. So if I have a plane, then there's a vector normal to this vector, which is like 90 degrees. If it is orthogonal to every vector in the plane, so I have a vectors in this plane, and this normal vector is orthogonal or perpendicular to each or to every vector in the plane. So I may have the vectors in the plane. This is P1, or here's P2. Those vectors are in the plane. And then I have a vector orthogonal to every vector in the plane. So this is 90 degrees. And we call this vector a normal vector. The easier example is that the vector k in the xy plane. So this is xy, right? This is the xy plane. And the coordinate vector k is perpendicular to every vectors in xy plane, right? So this is the normal vector to xy plane. Okay. Now, if I have a plane with normal vector, okay, this normal vector is not zero, not a zero vector, then this plane through the point with the vector p naught, how do we express the plane? We know that this is perpendicular to any vector in the plane, so the dot product should be 0. So the dot product should be 0. N dot product, your P minus P naught. That should be 0, and this 0 is a scalar. Okay. So if we want to express a plane with a scalar equation, we can use this idea, okay? Because the normal vector dot product with any vectors in the plane should be 0. Then suppose I have a normal vector, I have two vectors p and p naught. Those are in the plane. So n dot product p minus p naught will be A, B, C. P minus p naught, x minus x naught, y minus y naught, z minus z naught. Then I will get A x minus x naught plus b y minus y naught plus c z minus z naught. That should be 0. And this is your scalar equation of a plane. So I think probably some of you have already learned that in your senior high school. So here's the example. If I want to find the equation to express this plane. Okay, and this plane, because we may have this plane, this one, or here, right? But I want the plane through the vector p naught, suppose it's here. Okay, So I want this plane. And I know, and also because this is P naught, I may have a plane like that or plane like that, but I want the normal vector is 3 minus 1, 2. So maybe I need, this is my normal vector. Then I need to find that plane satisfy this. Okay, not this one. So with the normal vector, and I need a plane go through the P naught, then this plane should be 3 x minus 1 plus minus 1 y minus 1 plus 2 z minus 3. Okay. Any questions for this one? And then you can do it at home. Okay. So giving you a vector with a normal vector, then try to find the equation of the plane. Next one is called the expansion theory. What is the expansion theory? In the vector analysis or matrix analysis, we will, or linear algebra, we will see so many theories. Okay, so you can try your best to understand those theories. First, we say that those vectors is a set, and it is the orthogonal basis of a subspace of Rn. And x is any vector in this subspace. How can I express this x? Using this basis. Remember that what is basis? They are linearly independent, right? So each of them should be orthogonal. So the x can be expressed by the orthogonal basis. This is the vector, okay, and linear combination of these vectors. This is the magnitude or constant. For example, in the x, y, z, we can say that vector v is 5j. V is 3i plus 5j minus 7k. Right. First, I, j, k are orthogonal bases. Okay. And 3, 5, minus 7 will be their coefficient. How do we get 3? Since they are orthogonal, to get 3, I can have v inner product I, or dot product I. That will be 3i, the norm of I plus 0. Okay, so how do we get 3? V inner product I divided by I here. Okay. Let's write it down. Since F1, F2 to Fm, they span the subspace U. If we remember that if we say it spans if we span the subspace U, that means I can have any other vector. I can express any vector with a linear combination of those vectors F1 to Fm. So it could be C1 F1 plus C2 F2 to Cm Fm. And for this Ci, those are scalars. Just think about that. V equals 5i plus 3j minus 8k. Okay? So how do I get C1? How do I get 5? To get 5, V dot product I. Right? Because I dot product I, this is 1. And others, because they are orthogonal, so they are all 0. So to find C, to find C1, X dot product F1. So X, what is X? C1 F1 plus C2 F2, the linear combination of the orthogonal bases. And then at times in the dot product F1. So I get C1 F1 dot product F1, C2 F2 dot product F1, and so on to Cm Fm dot F1. Then continue. This is C1 F1, the norm square. Here C2 F2 dot the product F1 will be 0 because they are orthogonal. And similarly for the rest. Okay, so Cm Fm dot product F1, because they are orthogonal, so the inner product or the dot product is 0. Then we get C1 norm of F1 squared. And we know that for this equation, F1 is not 0. Okay, we know F1 is not 0. So the norm is not 0. Then we can get C1. Since F1 is not a 0 vector, then we get the coefficient C1 as the inner product or the dot product of X and F1 divided by the norm of F1 squared. So similarly, for each scalar or each coefficient, that is just your vector dot product their corresponding basis divided by the norm of that basis squared. And you can see the expansion of X. Is a linear combination of the orthogonal bases. And we say this orthogonal basis F1 to Fn to Fm. This is called Fourier expansion. Fourier expansion of x. And the coefficient Ci, this is called Fourier coefficient. Ci x dot product your corresponding basis divided by the norm of that basis squared. This is called what? Fourier coefficient. If you are not quite sure about this theory, just remember that my example, I have a vector. This vector for like 3 dimension, 3i plus 5kj plus 4k. Okay, I can express the vector with the linear combination of your orthogonal bases I, j, k. And then to get the coefficient 3, how do you get 3? V dot product I. Because V dot product I dot product I plus 5j dot product I plus 4k dot product I. Because they are orthogonal, this is 0, this is 0. And I dot product I, this is a unit vector, so the norm is 1. Then I get the coefficient. Okay, so if you can express a vector by the linear combination of your bases, then that'll be easier to get your coefficients. Okay. You inner product or dot product the bases individually. If you take signals and systems or some control theories later, you will use this a lot. Last part for the vector analysis, then we will talk about the metrics. And this one is also very important. The Gram-Schmidt orthogonalization process. So what is the Gram-Schmidt orthogonalization? You see, what is the orthogonalization? That means I want to convert the basis, this basis, to an orthogonal basis. So first, what is the basis? Back to, okay, with the basis, they are just linearly independent. That's it. And every other vector can be expressed as a linear combination of the bases. But to get the orthogonal basis, we have some method. For example, like 1, 0, 0, 1 is the basis, right? And they are orthogonal. But for the basis, it could be 3, 0, 3, 2, or -1, 4. It could be the basis because any other vectors can be expressed as a linear combination of these two vectors. Then this two will be the basis. They are not necessarily orthogonal. Okay? So as long as you can use two vectors to express any other vectors, then those vectors are called bases. Okay? But if you want the orthogonal basis, because orthogonal basis, you can do a lot of things later. If you want the orthogonal basis, then here's the process. you can, based on your original basis, to convert it to the original, the orthogonal basis. Okay, so suppose I have a basis V1 to Vn. V1 to Vn, I want this basis, I want to convert that to an orthogonal basis. To convert it, and here is the formula. Let's take a break and then we continue. Right, back to the Gram-Schmidt orthogonalization process. Basically, I want the basis to become an orthogonal basis. So how do we do this? Suppose I have so many vectors. So for this so many vectors, we choose a base vector, say V1. So my V1 just F1. Okay, I want vectors finally be orthogonal. Okay, so there'll be F1 to Fk. So I randomly choose one vector, say V1, and V1 is F1. How can I get V2? We need to delete the portion in the direction of V1 of F1. To get V3, I need to delete the portion in F1 and F2. Then the rest will be orthogonal to the vector F1 and F2. So, for example, I have V1 and V2. Okay, suppose I have a V1 and V2. This is V1 and V2. First, we need to choose what's in 2 dimensions. Okay, I have 2 vectors. 2 vectors could be the basis. All right, so any other vector can be expressed as a linear combination of V1 and V2. Now, to find the orthogonal basis, first we need to choose just randomly choose a base vector. Then, so here, let's see, V1, would you say choose V1 as F1? Now, my second vector should be perpendicular to F1, or we say V1. So we know, we just learned that the V2 can be projected to the direction of V1 or F1. So this is the projection. And this one will be perpendicular to that projection. So how do we get the projection? V2 inner product F1, which is just V1, okay, divided by the norm squared, the norm of F1 squared, then times the direction is F1. And this is F2. And the F2 is the blue one. F2 will be your V2 minus this part. Okay? Or then in that case, we probably just copy it. Copy. Paste. Okay? Then we have 2 vectors, F2 and F1. So here, F1 and F2. Will be the orthogonal basis. In the beginning, our bases are V1 and V2. And then after the orthogonalization, F1 and F2 will be another basis, and this basis is orthogonal basis. Okay. It is in 2 dimensions. Let's see if we have a 3 dimension. 3 dimension, I can have any 3 vectors to form a basis. Well, the orthogonal basis is that the coordinates, right? X, y, z. Okay, but I can also have a random basis as long as those three vectors are orthogonal, are linearly independent, and any other vector can be expressed as a linear combination of these three vectors. Then we call these three vectors are the basis. But to form orthogonal basis, these three vectors should be perpendicular. Then if I have copy and then paste, if I have another vector v3, now in 3 dimension, this 3 will be the basis, but not the orthogonal basis, because even though these two are orthogonal, but v3, this angle is not 90 degree, and maybe this angle is not 90 degree. So I need to form the basis, orthogonal basis. Then I need to deal with this vector v3. So again, because v3 can be expressed, we can think about the v3 will be something f1 plus something f2 plus something. This one is what we want. We need to get rid of the portion in f1 direction and f2 direction. So first, I can also project v3 onto we want to get rid of the part in f2, so they can project to the plane. When we project, I always have something parallel with the one direction, and the other one is perpendicular to that direction. So here I'll project to the direction of f2. So suppose I project to the f2, because it's too small, so I project to that. So here is the projection, right? And the other one will be the perpendicular one. To get this projection on f2, we have v3 dot product f2 divided by the norm of f2 squared, and the direction is f2. Then the orange one will be v3. Now the v3 project onto f2. So here I have a v3 minus the parallel one. All right. The orange one should be v3 minus the vector in the f2 direction. Then I can make sure that this is perpendicular to f2. Okay. Later on, I need to focus on this the orange one. The orange one, I still have some components in this vector. I have some components from F1, so I need to deduct that. I need to remove that part. So to remove that part, this one is something that in F1 direction, and the rest will be F3. To get this part, okay, this is V3 in the product or dot product F1 in F1 direction. Then my F3, I will have my V3 minus and then minus let me just finish this first. All right. Then my F1, F2, F3 will be perpendicular, and they will form as a orthogonal basis. In your homework, then this could be one of your application that you can investigate. And I can tell you that this one will definitely in your exam. So let me say this again. Suppose I have 3 vectors or n vectors, 3 vectors, for example. They are just the basis, not orthogonal basis. I want to form an orthogonal basis. First, I just choose one vector as our base. Then the second one, a second vector, I need to remove something, the part of the direction in this, say, A1, A2, A3. A1 is the base. A2, I want to remove the portion in the direction of A1. When I remove or deduct that portion, then these 2 vectors will be perpendicular. Okay. And for A3, the third one, I also need to remove the portion from A1 direction and A2 direction. Once I remove these 2 directions, then another vector, this F3, this vector will be perpendicular to F2 and A1, which is F1. And then I formed an orthogonal basis. Okay? Because when you deduct that portion, you see the addition of the vector. This vector A will be equal to vector B plus vector C. Right. So once they deduct the portion, then the rest will be perpendicular to your original vector. Okay. So first, choose one vector, good. The second vector, the second one, minus or remove that vector in the previous vector direction. And the third one, remove the portion from the previous two vectors till the kth one. Okay. We will say F1, F2 till Fm is an orthogonal basis of the vector space V. And we can say that the span. You can express any other vector in terms of, with a linear combination of your orthogonal basis or your original basis. They are the same. So we say that span F1, F2 to Fm. This will be also equal to the span V1, V2 to Vn. Oh. It should be Vn. So this holds for each k. Okay, just think about, I can express any other vector in this coordinate form. Those are the orthogonal bases. But I can also make another basis that are not orthogonal. So maybe 1, 2, 3, here is 4, 2, 0, and 3, minus 2, and 4. Maybe these three are also the bases, but they are not orthogonal. But any other vectors can be expressed as a linear combination of either this basis or orthogonal basis. Okay. Let's see this example. In 2 dimensions, these two vectors are the basis. So if I want to express 4, 2, to express this vector 4, 2, 4, 2 will be A plus B, right? Linear combination of A and B, because A is 3, 1, and B is 1, 1. So if I add these two together, there'll be 4, 2. Okay, A and B are the bases, but they are not orthogonal. I want to find the orthogonal basis. Then how do we find that? In the beginning, that we will choose one of our original vectors as a base. So we say F1 is the vector A, which is 3, 1. Now to find a vector that is perpendicular to F1. So I need to use the other vector B and remove the portion in F1. So here B, projection of B on F1. which is 1, 1 minus 4 over 10, 3, 1. And we say that F1 and F2, this set is an orthogonal basis. So maybe you thought like 1, 0, 0, 1 is the orthogonal basis. That's correct. But to convert these two vectors as a basis to the orthogonal basis, the final answer is not just 1, 0, 0, 1. Okay, it should be 3, 1 and here. It looks like this is 1, 0, 0, 1. Okay, but I rotate. So this is also 90 degrees. So it could also be the basis, could be the orthogonal basis. Okay, this probably will be, probably is the example of this one, 3, 1 and minus 1 over 5 and 3 over 5. Okay. To get the orthogonal basis, then it would be easier to find their coefficient, because any other vector, say C, can be the linear combination of your orthogonal basis C2, B. Easier to get C1, C2 because they are orthogonal. To get this coefficient, C1 will be C in the product A divided by the norm of A squared, because when A dot product B, there'll be 0. That's why that people love the orthogonal basis. All right, let's see the case in 3 dimensions. Okay, in 3 dimensions, and we need one more. Okay, so I have 3 vectors, and then A, B, C forms a basis, but I want to find the orthogonal basis. So first we can choose A vector as our F1. You can choose B or C, it doesn't matter. Okay, if you choose B or C, then finally your answer will be different. So F2 will be your vector B minus the portion in F1, some component in F1. So I want to get rid of that component. So you have 1, 2, 2 minus 5 over 3. At home, you can also try that, getting B or C as our base first, and try to find the rest too. Then you should get minus 3 over 2 over 3, 1/3 and 1/3. And the next vector, F3, we need to deal with the vector C. So I want to remove the components or the portion in F1 and F2. So C dot product with F1 here should be F1 and F2. So you get 1, 1, 0 minus 2/3, 1, 1, 1, and minus 1/3, and here's 6/9 minus 2/3, 1/3, 1/3. So your answer will be 0, 1/2, 1/2, minus 1/2. Okay. Remember that at home, try to use B as our first base to find the orthogonal basis, or C. Or you can still use A first, but your second one, you chose C. Here will be C, and this one will be B. And to find your answer, okay? So, any questions so far? Now that is just all for the vectors.